Hello, everyone. This is the third video that I'm recording as part of the AWS Machine Learning Specialty Exam Prep course. And today we'll be covering the third exam section, which is about modeling. And it's the biggest and the most important section, which weighs around 36% out of the whole exam. So this section, it focuses on basic data science topics that I believe everyone who has been working on the field they should know about. So we're gonna aim to review like basic topics and build on that in order to go into advanced topics on this section, which is mainly about AWS SageMaker, which constitute around half of this section. And you should expect to have lots of questions around SageMaker, built-in algorithms, etc. So as a description of this section, it focuses on model selection and evaluation, training and fine-tuning models, model deployment and monitoring, and model optimization. It also tackles various ML algorithms and other services available in Amazon SageMaker for model training and deployment. So it's like as I said, it's the most important section and has a lot to do with model development, training, fine-tuning, and deployment using AWS SageMaker. So the strategy is as before, is to cover the main content, and then we're gonna end up with sample questions which help us to test our knowledge and to give us a taste of real exam questions. The main topics that will be covered in this section can be summarized in this slide. We're gonna start to talk about the end-to-end machine learning cycle. Then we're gonna review the types of machine learning solutions, supervised, unsupervised, and deep learning. Then we're gonna spend some time talking about machine learning performance matrix. And then we're gonna move into AWS SageMaker, where we're gonna give an overview of AWS SageMaker architecture and features. And then we're gonna talk in depth about AWS built-in algorithms and what are the options for training, deployment, and hyperparameter optimization in SageMaker. And we're gonna end with AWS Autopilot and Canvas solutions or services, which are also available as part of SageMaker. So, the first topic that we're going to talk about is end-to-end machine learning cycle. So this graph, it summarizes the different stages that almost, I would say, every machine learning project goes through. So first of all, we start with the business goal, which is what we are trying to achieve out of this project. So after we have the business goal, then we take the goal and we frame it in ML problem, which is like, are we trying to solve classification problem, regression problem? This is what we mean by ML problem framing. And then after we frame the problem, then we gather the data and we start doing data processing. And after we do the data processing, we can start developing the model. But sometimes when you develop the model, you discover that you need more data, or you need to further work on processing, on transforming the data. So you need to go back to data processing and then go back to model development. And then after model development, and when we have a model in place and we did evaluate the performance of this model and we are fine with it, we move to the second stage, which is model deployment. And after model deployment, we're gonna think of monitoring techniques in order to monitor this model when it runs in batch or in real time in order to make sure it's giving reasonable and accurate predictions. And after we have the monitoring, sometimes you go back to model development in order to refine the model, deploy it again, and have monitoring results. So as you see, these steps are not like one-way steps. sometimes you will be doing model development and then you need to go back to the processing, and sometimes you are doing monitoring and then after the monitoring you need to further refine and develop the model. So within each step you will be thinking of the previous steps and how to improve the model performance in order to enhance the achievement of the business goal. So you need to go back and forth in order to make sure that your project is going on the right way and you are solving the problem that your client or your stakeholder has communicated for you. So to sum it up, first of all, you start with your business goal that aim to achieve? Is it like to increase sales by 5% or to decrease the amount of fraudulent activity by 10%? This is like what's the impact will be on the company or in business activity. Then you take this business goal, you transform it into ML problem, and then you start to gather data, process the data, build the model, evaluate the model, and when you are fine with the model development, you move to deployment to take it to the end user. And after deployment, you need to think of monitoring or evaluation mechanisms in order to make sure that the model predictions are accurate and reasonable. So, what are the types of machine learning solutions? Uh, it could be summarized into below. We have supervised learning, unsupervised learning, and reinforcement learning. And I'm pretty confident that every data scientist who has some experience, they would know the content that we're gonna cover in this slide and in the upcoming slide. But it's also good like to give a refresher and make sure that everyone has the necessary foundation before we go into the advanced topics of AWS SageMaker. So the types of machine learning solutions, it could be summarized as below: supervised, unsupervised, and reinforcement learning. Supervised learning is a type of ML where the algorithm is trained on a labeled data set to predict continuous variables such as regression, or to predict categorical variable when we talk about binary classification or multi-class classification. So supervised, you need to know that supervised, when you have labeled data set, you have like a labeled target variable. And if it's continuous, so if you are predicting, for example, the amount of sales for next year, we are talking about regression, or if you are predicting like the customer type, or if you are predicting if this customer will churn, yes or no, this would be binary classification. Or if you are predicting like the category of customer review, this would be multi-class classification. The second solution would be unsupervised learning. And for unsupervised learning is when the algorithm is trained on unlabeled data set. So you don't have a labeled target variable. And you use this unlabeled data set to find patterns, clusters, or relationships. Examples include clustering and dimensionality reduction. And the third ML solution is the reinforcement learning. And it's when an agent learns to make decisions in an environment to maximize a cumulative reward over time. So these are the three main types of ML solutions. We're going to talk a bit further about it. So within the supervised learning, we said we have regression, and regression is used when you want to predict continuous variables. Some examples include, such as given values advertising spend, predict the sales for next year. This is a regression problem. Second example could be given characteristics of the couple, predict the matching probability, such as, and this is like a recommendation system in dating apps. This is also a regression problem. On the other hand, we have classification, and classification is used to predict categorical variables. As I said earlier, we have binary class when you have two classes, like true or false, versus multi-class classification, you have when you have more than two classes. And examples could include, for example, detect fraudulent activity in credit card transactions. Here we are detecting if it's fraudulent or non-fraudulent. So this is binary class classification. Or if you want to classify customer reviews into various groups, such as payments, complaints, inquiry, billing, customer experience, and could be a multi-class classification problem. So for unsupervised learning, as we said earlier, we are training an algorithm on unlabeled data set. Examples could be clustering or dimensionality reduction. Clustering is used when we want to find subgroups or structure information and derive meaningful relationships from data. Examples could be when we want to do customer segmentation and segment customers into groups with similar preferences in order to be targeted with tailored marketing, for example. And another example could be to identify topics in a set of blog posts and to know also what customers will be talking about. For example, a new launched product, talking about customer experience, etc. And another type of unsupervised learning is dimensionality reduction. And dimensionality reduction is a commonly used approach in feature processing to remove noise from data. When you have like a huge amount of data and you want to like reduce the dimensions of this data, but at the same time retain the information that is available in this data set, you can apply dimensionality reduction, where you transform high dimensional customer data into a lower dimensional representation that still captures the essential patterns and variations that you want in order to train machine learning algorithm. Uh, Reinforcement learning, as I said, it's used like to develop a learning system, okay, which is called an agent in this context. And this agent will observe the environment, will select and perform actions, and get rewards or penalties in returns, depends on the outcome of the action. So a very like popular successful reinforcement example would be the DeepMind's AlphaGo program, which was developed in March 2016, and where the where this program, the AlphaGo program, did beat the world champion and at the game of Go, and where what happened there, it's like this program or enforcement program, AlphaGo program, it did learn the winning policy by analyzing millions of games, and when this program did play against the champion, sorry, it ended up like winning the game against him. And the thing is, or the key here is like this learning system or this agent is learning the actions by going, and as we give it more rewards, he would know that it's doing the right action, and if we give it penalties, he would know that we are giving it's doing like a unappropriate or the wrong action, and it will give it negative rewards. So this is how it learns. It learns by itself, but also by giving it rewards or penalties in returns. So this is a summary table of ML types. We said we have supervised, unsupervised reinforcement learning. Within supervised, we have labeled data, and we are predicting outcome or future. We also said we have regression and classification. For unsupervised learning, we are talking about unlabeled data set, which doesn't have targets, and it's used to find hidden structure in data, such as clustering or dimensionality reduction. And the third ML type is reinforcement learning, where it could be considered as decision process or reward system, where it learns series of actions based on awares or penalties. The second topic that we're going to talk about is deep neural networks. And like deep learning has gained a lot of attention in the previous years, and it's developed to design and simulate the behavior of a human brains, interconnected network of neurons. So just like it tries to model or replicate how the brain would work, we do it with neural networks, and it becomes so popular in the previous years because of the high generation of data, because we have huge availability of data, which would make deep neural networks more successful. And the second success factor would be the high availability of computational power, because these deep neural networks, in order to be trained, it needs high computational power. So if we cover a bit about the deep learning components, we can see that DNNs have multiple hidden layers between the input and the output layers, which gives them the ability to learn the representations of data in a more complex way. So each layer were increasingly abstract features or concepts, so it will learn more, allowing the network to capture complex patterns and relationships where classic machine learning might fail. So this is why we use deep neural networks. Deep neural networks have something what we call activation functions, and these activation functions, it defines the output of a neuron given its input signals. So it's good to know that in case of binary classification, we have sigmoid activation function, and in case of multi-class classification, we would have softmax activation function. So sigmoid is activation function used in case of binary classification, and softmax is an activation function used in case of multi-class classification. There are different deep learning architectures that everyone should be aware of, such as CNNs or convolutional neural networks, and which is used for image and video processing, such as image classification. We have RNNs or recurrent neural networks, and which is used for sequence data processing, such as machine translation. And we also have JNs or generative advisor networks, which is being used for generating new data examples. So some of the modern deep learning architectures are CNNs, RNNs, and JNs. Uh, some important concepts also in the context of deep learning, we have learning rate and batch size, and these are like hyperparameters. Learning rate is the hyperparameter that determines the step size of weight updates during optimization in model training, whereas batch size is another hyperparameter that defines the number of training samples used in each iteration of the optimization algorithm during model training. So learning rate and batch size, in other words, are hyperparameters that control the model training process. Important like details that we should know about these two hyperparameters. We should know that small batch sizes are good to prevent not converging the problem in the wrong solution, because if we use large batch sizes, we can converge the model in the wrong solution and it gets stuck in the local minima. On the other hand, large learning rates, if we use large learning rates, can overshoot the correct solution and which oscillates and miss outliers. Whereas small learning rates are better, but at the same time, they increase training time, or like it takes more time for the model to be trained. So as a rule, we should opt for low learning rates and or small batch size while defining these hyperparameters in the model training process. So we should aim for low learning rate and small batch size when defining the parameters when defining the hyperparameters in the model training process. Some techniques to apply regularization or to control overfitting, because sometimes overfitting means when we train a model and the model performs very good on the training set, but it fails to perform well on the test set. So the performance would be so different between train set and test set, and this is what we call overfitting. And in order to control overfitting in the context of deep learning, we can think of the below 4 strategies. First of all, to apply dropout, or to apply early stopping, or to apply L1, which stands for lasso, and it's sum of weights. And lasso, it's good to know that it's used for feature selection, because what does lasso do? It brings some variables to 0. And the fourth technique would be to apply ridge, or L2, and it is the sum of square of weights, which reduces the impact of less important features, but it doesn't bring some variables to 0. So the main difference between L1 and L2, L1, it's used for feature selection because it brings some non-important variables to 0, whereas L2, it keeps all variables or all features, but it assigns weights, which are not 0, unlike L1, okay? The next topic that we're going to talk about is machine learning performance matrix. So we have different performance matrix which differ between ML solutions if we're talking about regression or classification. But if we're talking about classification, we can think of a confusion matrix, which is simply a table that summarizes the performance of a classification model by comparing predicted and actual class labels. Within the context of confusion matrix, we can think also of precision, which is helps to evaluate the assertiveness of correct positives. And precision can be computed as true positive divided by true positive plus false positive. Recall, and which is known as sensitivity or true positive rate, it gives the importance, or it provides an insight about the importance for real positive cases. And it can be computed as follows: true positive divided by true positive plus false negative. Uh, Another performance metric which you should know about is F1 score, and F1 score is used when we want to take into consideration the assertiveness of both positive and negative classes. It's known to be as harmonic mean of precision and recall, and it's calculated as follows. It's 2 multiplied by precision and recall divided by the sum of precision and recall. And for the exam, we should know each what each of these performance measures do, and you should know how to calculate as well, because they might give you a question to calculate F1 score. They might give you confusion matrix and ask you to calculate F1 score or recall or precision. So the question that we should ask ourselves: who want to use precision or who want to use recall? So we should use precision, or we should choose precision as our ML performance metric when we want the prediction of positive classes to be correct as possible as we can. Examples or business examples could be if we are applying YouTube recommendations, we should use precision. If we are applying a model to predict the criminal death punishment or spam detection or loan applications, in these examples, we should aim to use precision. On the other hand, we should aim to use recall when we want our model to spot as many real positive classes as possible. So when we want to reduce false negative, in other words, we should aim to use recall, such as if we're developing a model to predict cancer or to detect cancer, then in this case, we should aim for recall because we want as many as real positive cases to be detected by the model. Fraud detection, another example, or if we're developing a model to detect unsafe work images as well, because this affects people's life, then we should also aim for recall. Uh, the two other ML performance metrics that we should know about are ROC and AUC. And ROC stands for Receiver Operating Characteristic Curve. And it's a plot of true positive rate, which is the recall, versus the false positive rate at various threshold settings. Ideal curve of ROC would be a point in the upper left corner. And ROC is better used when both outcomes have equal importance. So if the question entails that both outcomes or both classes have equal importance, then we should think of using or choosing ROC. AUC, on the other hand, it's the area under the ROC curve. It's equal to the probability that a classifier will rank a randomly chosen positive instance higher than a randomly chosen negative one. So if we have AUC of 1, this means we have perfect classifier, and I doubt someone will get there. 0.5 means we have useless classifier because it has the same probability of choosing positive or negative, which doesn't make sense. And AUC is best used in case of imbalanced class distribution. So if we have a data set with classes which are imbalanced, then we should think of using AUC. So this takes us into the end of covering the basic ML concepts, which ML performance matrix, what are the types of ML solutions, and now we'll start talking about AWS SageMaker. And AWS SageMaker is a fully managed machine learning service that's available in AWS platform and that developers and data scientists can use to build, train, and deploy models. So it's one service or platform which helps to do end-to-end ML project from building the data set, doing pre-processing, training a model, and fine-tuning the model, and then deploying the model. It's all available in SageMaker. And as we see in the upcoming slides, we have features which cover all the ML project cycles. So if you want to give like a brief overview of what SageMaker is about, SageMaker helps us to fetch, clean, and prepare data. So this is the first step of ML project. Then it helps us to train and evaluate a model, which is training and fine tuning. And then we can deploy the model, evaluate results in production. So as I said, it can cover almost all the project cycles from fetching, cleaning data, pre-processing, and transformation as well. Then to move into choosing ML algorithm, training the model, evaluating the model using proper ML performance matrix. Then when we want to deploy the model, bring it to production and bring it to the end user. Also, we can evaluate the model in this stage, and then we can also repeat the same exercise in order to keep refining and improving the model that we have in production. So, what's the SageMaker architecture? Here we see that SageMaker, it uses S3 and ECR, which stands for Elastic Container Registry. So we see that the model training and the model hosting, it's being done within SageMaker, but we also use S3 to load S3 model to load the model artifacts. For example, if we are using a model or of using like AWS built-in algorithm, we can load the artifacts or the model artifact from S3, and we also can load the training data from S3. So S3 is used to load the model artifacts and to load the training data or the testing data. And then we do the model training within SageMaker. And we also need the training code image, which also being loaded from ECR or Elastic Container Registry. And then after we do the model training, we evaluate it and we are good, we are ready to deploy the model or to host the model. And for model hosting, we need the model artifacts from S3, which are the artifacts of the trained model. And we need the inference code image, which also being loaded from ECR. We host the model within S3. We create an endpoint if we are talking about real-time prediction, which is being loaded for client app up to the end user at the end. So to emphasize on some points, so we need to know that S3 is being used to host or to save the artifacts of the trained model. It's being used to save training data as data. We load the training data from S3. We do the training on SageMaker, and we load the trained model artifacts from S3 and the inference code from ECR. We do the model hosting within SageMaker, and then we create the endpoint. So what do we need from S3? We need the model artifacts and training data. And what do we need from ECR? We need the training code image and the inference code image. And the model training and the model hosting and the endpoint are being created and hosted within SageMaker. So, as I said earlier, so SageMaker includes features which are relevant to the different phases of machine learning. So if we are talking about data preparation or processing, we can think of ground truth, data wrangler, processing, feature store, and clarify. If we're talking about building the model, we have tools such as notebooks, Studio, Autopilot, Jumpstart. If we're talking about training and fine-tuning the model, we have managed trainings, experiments, tuning, debugger. And when we want to deploy the model, we have managed endpoints, model monitor, pipelines. So probably will not have time to discuss all of these topics, but what I do advise you is like to go to AWS SageMaker documentation and try to know what each of these features do, and when to use it, uh, in which phase of the machine learning, and how to use it. Okay. So, some of the topics that we're gonna talk about are definitely notebook instances, and notebook instances are managed machine learning compute instance, which EC2 instance, which runs on Jupyter server. It has access to S3 if you want to load the training data, test data, or if you want to save the model artifact at the end, or if you want to save the preprocessed data, if you are doing data processing. So it has access to S3. We can use scikit-learn, Spark, or TensorFlow within these notebook instances. It has wide variety of built-in models, which we're going to talk about in a bit. It has the ability to spin up training instances of our choice, and it has the ability to deploy trained models for making predictions at scale. So this is what notebook instances is SageMakers do. So to create your notebook instance, these are the things that you need to think about while creating your notebook instance. You should think about the EC2 instance, which is being spun by virtual machine, and you need to choose which family this EC2 instance should belong to. And within that, you have TMCP. T C stands for compute optimized, and P stands for GPU. So if you want for training like a deep learning model which has like million or billion of parameters, then you have to go for GPU. If you are training like a regular ML algorithm, you can go for C, compute optimized. And then, other than the family of this EC2 instance, you should think of its size. You have medium or X large, and you have like medium, large, X large. You need to choose, and you have to choose the right version of the EC2 instance, and which is like ML.T3. You have T4, T5. It depends. So, while choosing the EC2 instance, you should think of the family, size, and the right version. You also need to think of the EBS volume to store data, and it can be ranged between 5 gigabytes, which is the default one, into 16 terabytes. You also have the option to do something which we call lifecycle configuration, and it's simply a bash script which you can develop in order to create or start a notebook, and to make notebook to run at specific time, and to install some packages. So lifecycle configuration helps you to create, start, and run a notebook using bash script, and it also helps you to install packages which are needed to run this notebook. The last thing is the elastic inference if you want to attach it to the notebook instance, and elastic inference allows you to attach low-cost GPU to SageMaker instances in order to reduce the cost of running inference. So these are the things that you need to know while creating your notebook instance. You need to know what family, size, and version of the EC2 instance you want to use to spin by virtual machine. What's the EBS volume? If you want to use lifecycle configuration, and if you want to attach elastic inference. SageMaker Studio, we can think of it as like web-based IDE for machine learning, which has Jupyter Lab environment. Within the SageMaker Studio, you have the visual Git workflow. You have the option to do experiment tracking if you are testing different models. Within SageMaker Studio, you also have SageMaker Autopilot, which we're going to talk about later in the video, which is used for AutoML on tabular data sets. You also have something which we call SageMaker Jumpstart, and within SageMaker Jumpstart, you can have like curated one-click solutions for applications without ML knowledge. You can have building pipelines. You can use Clarify, SageMaker Clarify, which is used for detecting pre-training bias. You can have feature store to help you create, share, and manage data, and you can have data wrangler to prepare the data. So these are all the features which are available in SageMaker Studio. IDE, web-based IDE, Jupyter Lab, Git workflow, experiment tracking, autopilot, jumpstart. I also advise you to go and read the documentation of SageMaker Studio and see what are the available features there and what does each feature help for. Okay. Now we're gonna talk about the built-in algorithms of AWS SageMaker, which is also very important topic for the examination. But before going there, let's reiterate reiterate some concepts of the end-to-end ML cycle, and then try to break down the machine learning problem. So to break down the machine learning problem, I would say the most important step is to know the use case or the business goal, what we are trying to achieve here. For example, are we trying to achieve fraud detection? After we determine the business goal or the use case, then we need to look into what data do I have? Do I have structured data, numeric, continuous, or do I have unstructured text data? After I navigate or explore the data options I have, then I go to option number 3, which to choose which model should I use, or which ML solution should I follow. Should I follow supervised, unsupervised, or deep learning? After I determine which model or which ML solution should I take, then I can frame the problem to use models I know. So how do I frame the problems? Should I use regression, classification, clustering, or reinforcement learning? So to break it down, first of all, you need to know what's the use case of the project that you are working on. What are the available data you have? Which ML solution or which model should you use? And after that, you need to frame the problem in a way that you can apply ML. In this slide, I'm just like summarizing all the built-in algorithms of AWS SageMaker. Each model solves prediction problem, and I do advise you also to go into the AWS SageMaker documentation and to go over all the available algorithms that are being developed, because this list might be extended in the future. But if we go for classification, for example, you need to know that the most prominent built-in algorithms for classification are linear learner, XGBoost, KNN, and factorization machines. If we are talking about computer vision, we have image classification model, object detection, and semantic segmentation. If we are talking about topic modeling, you have LDA and NTM. For forecasting, you have deep AR. For recommendation, you have factorization machines. If you are working with text, you can think of Blazing text algorithm. For regression, you have linear learner XGBoost. And for sequence translation, you have sequence to sequence. And for clustering, you have K-means and KNN. So the prediction problems could be computer vision, recommendation, forecasting, regression, etc. And for each prediction problem, you have different algorithms that you can use. We're gonna talk a bit about some of these algorithms, but as I said earlier, I advise you to go into the AWS SageMaker documentation and to look into each of the to read the documentation of each of the algorithms that are available, and you need to know what's the use case of this algorithm, what kind of pre-processing is needed before using this algorithm, what are the main hyperparameters of this algorithm, and how to train this algorithm. So 4 things which I advise you to know ahead of time is the use case of the algorithm. Is there any pre-processing needed for the training data in order to use the algorithm? What are the most hyperparameters which boost the performance of this algorithm? And is there any special consideration that we need to know for training? Does it need CPU or GPU? So linear learner. Linear learner is an algorithm which is used in either regression or classification. And it like resample, or like it reflects the way that simple regression would work, and which is to fit in line to your training data. For linear learners, you should normalize the data. So normalizing is an important preprocessing step before using linear learner. So you need to make sure all the features are weighted the same. The most important hyperparameters of linear learner is balanced multi-class weights, learning rate, many batch size, L1, and weight decay. And this is only like some of the hyperparameters. Like there are others. I also advise you to go and to read what does each of these hyperparameters stand for. And for training the linear learner, you can either use single or multi-machine CPU or GPU, depends on the amount of data or the volume of data you have. The other algorithm that we're going to talk about is sequence to sequence, or like if you have input output sequence of tokens. The use cases of this algorithm is machine translation, text summarization, or if you are developing speech text solution. Framework, it's implemented with RNNs and CNNs with attention, and it uses pre-trained model like BART or T5. The most important hyperparameters of sequence to sequence are batch size, learning rate, and you can optimize on accuracy, BLEU, or perplexity. For training this model, of course, you need to use GPU instances. You can use P3, for example. Deep AR, it's used for time series forecasting, and it helps us to find frequencies and seasonality in the data. The framework is simply you need to include the entire time series for training, testing, and inference, and you can train on multiple time series. This is the one uniqueness of DeepAR, which helps you to train on different or multiple time series. The most important hyperparameters of DeepAR are context length and prediction length. Context length is the duration of time you need to look into in the past, and prediction length, how many days or weeks you want the model to predict for the future. Epochs, learning rate, and many batch size are the other important hyperparameters. And for training, you can either use CPU or GPU. The next built-in algorithm that we're going to talk about is blazing text, which is used for text classification and word-to-vec. And it helps to predict labels for a sentence or create a vector representation of words for translation or sentiment. The framework, the word-to-vec one, it has multiple modes, which are CBOO, or continuous bag of words, or skipgram. The hyperparameters are being used for text classification are epochs, learning rate, and word n-grams. And for training the blazing text, for text classification, CPU is recommended, but if you are implementing the word-to-vec solution, then GPU is better. So I also advise you go to the blazing text documentation, know what are the most important hyperparameters, what's the difference between word-to-vec and the text classification modes, and how to train this model. Factorization machine, which is used for recommendations. And the use cases of factorization machine is when we have sparse data. So whenever you see a question which entails sparse data, then you need to think of factorization machine. Popular business examples could be like to-click prediction and item recommendations. The framework of factorization machine is like when you have, or when given a matrix representing some pair users and items, to predict the click or not to click, or to predict like a rating of given products for a customer, what's the most popular or what's the prominent fancy product that we should advertise or give it to the customers. This is being done by recommendation engines, and which could employ factorization machines. The most important hyperparameters of factorization machines are number of factors and feature dimension. And for training factorization machine, because we have sparse data, we can think of CPU. So here I'm adding a summary of the built-in algorithms use cases. But also you have like a very extended summary on the AWS website or AWS documentation, which tells for each algorithm what are the best use cases. So if we have a use case to predict if an item belongs to a category, for example, spam detection, we could think of linear learner, XGBoost, factorization machine, k-nearest neighbors. If we are thinking of a use case to predict a numeric or continuous value, such as estimate the value of a house, we can also think of linear learner, which is being used for regression and classification, XGBoost, which also used for regression and classification. We can think of factorization machine, which also being used for regression and classification, and k-nearest neighbors. If you see, these 5 models can be used for regression and classification: linear learner, XGBoost, factorization machine, and KNN. If we have a use case to predict future behavior, like time series, or to predict sales on a new product based on previous sales data, we can think of deep AR. Um, if we have a use case to identify duplicate support tickets or find the correct routing based on similarity, we can think of object-to-vec algorithm. And if we have a use case, for example, to tag every pixel of an image individually with a category, we can think of semantic segmentation algorithm, which can help us to determine or to tag every pixel of an image individually with a certain category. So yeah, these are the main use cases, but you need to know for each use case what kind of algorithms, or the way around, for each algorithm you need to know what are the potential business use cases that you can apply for. The next topic is we're going to talk about is what are the training options in AWS SageMaker. And the training options could be summarized as using an algorithm which provided by SageMaker, like AWS built-in algorithm. We can use Apache Spark with SageMaker, or we can submit a custom code to train at SageMaker, or we can use our own custom algorithm with a Docker image, or we can use an algorithm from AWS Marketplace. So here I also advise you to go to AWS SageMaker documentation and to read thoroughly about each of these training options. What are the differences and what are the steps needed, for example, to train your custom code in SageMaker, or what the steps to use Apache Spark or MLlib within SageMaker. I would say the easiest one is to use an algorithm provided by SageMaker, which is simply loading the container of the model and then seeing what are the needed data processing, which should be followed before using the algorithm, and then ask the model to, or ask the algorithm to be trained on your data. Next, we're going to talk about deployment options on SageMaker. And with deployment options, we have two modes, which are endpoints and batch. For endpoints, endpoints are used as persistent endpoint for making individual predictions on demand. So if we're talking about predictions on real time, we should think of endpoints. And for endpoints, we can use multiple EC2 instances, with each instance have model artifacts and responding to requests from RESTful APIs. It's perfectly used for online referencing or real-time predictions. And the method to do it, you can create an endpoint and then call this endpoint.predict on whatever ask you have. And you can also use automatic scaling. So as the data or as the requests increase, you can use more compute instances. Second deployment option is batch transform. And batch transform, we use it when we want to get predictions for an entire data set. And when we want to run inference, which doesn't need a persistent endpoint. So if it's not endpoint, we can use batch transform, and we can use the lambda function to execute the code and start the batch transformer job on the entire data set. And the method to do it is we create a batch transformer job, which is called transformer, and we do transformer.transform in order to transform the data set and create predictions. The next topic we're going to talk about is hyperparameter tuning. And for hyperparameter tuning on AWS SageMaker, we can use random search and Bayesian optimization search. The first step you need to do is to split the data into train, validation, and test data sets. And this hyperparameter tuning, it allows us to find the best values, for example, for some of the hyperparameters, such as learning rate, batch size, or depth. We did cover this before. Learning rate is a hyperparameter that determines the step size at each iteration, and batch size determines the number of samples processed before the model is updated. And we use hyperparameter tuning to test every combination of every possible value somehow, then train a model and evaluate it every time and give us the best results. So it gives us the best results of the hyperparameters, which gives the optimal model performance. So for hyperparameter tuning, we need to define the hyperparameters and ranges. We need to pick objective metric and strategy, and we need to set up the job parameters. Here we're giving an example, and some of the tips for hyperparameter tuning: we shouldn't optimize too many hyperparameters at once. We should limit our ranges that we need to search for, and it's better to use logarithmic scales. And I forgot to mention that, but the two most, or the two hyperparameter tuning approaches available in AWS are random search, and Bayesian optimization search. Ground truth, we did talk about this in the first in the ADA section in the second video, which is labeling service. It manages the humans who will label data for us for training purposes. And within ground truth, we can create our own model. And as the model learns more, only data points that the model is not confident about can be sent to human labelers, which can reduce the cost for us, cost of labeling. And who can label? Mechanical Turk, AWS staff, or we can invite our internal team to do the labeling for us within the ground truth platform, or we can hire professional labeling companies to do the labeling for us. Autopilot is an AWS SageMaker feature which helps us to do AutoML, but with guidance and judgment, where we can give it raw data, which should be tabular data from Amazon S3. We select the target column for prediction, and then Autopilot will do automatic model creation for us, which will give us correct algorithm to use. Training and tuning is done automatically for the right model. We don't need to do the model tuning by ourselves. And also we have full visibility with model notebooks. So it will create the notebooks for us, fine-tuning script, etc. But we'll be able to see how this model is, how this notebook is being developed, and we can amend it and then deploy it again and monitor the model. Whereas Canvas, on the other hand, it's also AutoML solution, but it doesn't require any code or any knowledge of ML. It's used by business analysts. You can simply upload the CSV data, select the model to predict, and Canvas will build it for you and make predictions. It can be used in classification or regression, and it do automatic data cleansing for you, such as missing values, outliers, duplicates. You don't need to worry about that. Some of the prominent use cases for Canvas could be to predict employee churn, fraud detection, inventory optimization, sentiment, image classification, or in-time deliveries. Okay, this takes us for the end of the explanation of the content of the modeling section. This is very heavy section, and it has a lot of concepts that you need to be aware of. I would advise to take what we explained in this video as exploratory video for you, where you need to know what are the topics, and then you need to study more and read more about all the features of AWS SageMaker, what are the available built-in algorithms, what does each built-in algorithm help us to solve, what are the hyperparameters, how to train these algorithms, what are the training options, what are the deployment options, how to follow deployment, how to apply training. I would advise you also to go through some notebooks which help you to bring your theory into practice. And definitely you should make sure to revise all the basic data science concepts, such as what are the ML problems that we have, ML solutions, simple examples, how to evaluate a model, which performance metrics to use. These all are important concepts for the AWS ML examination that you should make sure you are confident to answer any question which comes through your way while sitting for the examination. And now we will go through some sample questions which help us to test our knowledge. Question number one. First of all, we need to read the question, look for keywords, and try to think of some potential answers before reading the answer choice. So you are working as data scientist for pharmaceutical company. You are collaborating with other teammates to create a machine learning model to classify certain types of diseases on image exams. Which type of metric would you use to optimize the underlying model? So the keywords that we should look into here is like we need to classify certain types of diseases on image exams. So here we are trying to like to identify disease. So it's like something which we need to be aware of true positive here. So we need to identify as much as true positives as we want, and we need to reduce false negatives. So in this case, we should think of recall. And if we look at the options that are available, recall, precision, R-squared, F1 score. So R-squared, it's not a metric which is being used in classification, which can take it out. And we still have F1, precision, and recall. But since we are working on a problem which entails diseases, and we want to identify as much as real positive as we want in this case, then we need to choose recall. So option A is the correct answer. Question number two, what methods of hyperparameter optimization does Amazon SageMaker provide? We did cover this in the previous slide. And for hyperparameter optimization in AWS SageMaker, we have Bayesian optimization and we have random search. So if you look into the options, option B, random search, is correct, and option D, Bayesian optimization, is correct. So B and D are the correct options in this question. Question number three, they are telling us a large consumer goods manufacturer has huge sales history of products available in Amazon S3. And currently the company is using custom-built autoregressive integrated moving average, which is a time series model, to forecast demand for these products. The company wants to predict the demand for new product that will soon be launched. Which solution would be machine learning specialist apply? Should a machine learning specialist apply? So the keywords that we should look into here have a huge sales history, okay, which entails we have different time series. We're using Arima, and Arima wasn't successful anymore, and they want to move to a new product that will be launched soon. So if we go into the options, we have first option, train a custom Arima model to forecast demand for the new product. Train an Amazon SageMaker Deep AR to forecast demand for the new product. Train an Amazon SageMaker K-means clustering algorithm to forecast demand for the new product. Train a custom XGBoost model to forecast demand for the new product. So because this is like a time series forecasting model and we have a huge sales history, then Deep AR would be a very good option here in order to train it and to focus the demand of the new product. So it will be the best option. K-means is not being used for time series, and they were using Arima before and they want to move away from Arima, so option A wouldn't be useful. Option C is not useful, and option D, custom XGBoost, will be like more time consuming, so we can simply load the deep AR algorithm and use it as a forecasting model to forecast the demand for the new product. So option B is the correct answer here. Question 4, they are telling us you are working in a machine learning team to build and plan to operationalize a machine learning model that uses deep learning to recognize and classify images of potential security threats to important government officials using skills taken from live security video. So we're taking data from live security video. However, when your team runs their many batch training of the neural network, the training accuracy oscillates over your training epochs. What's the most possible cause for your training accuracy problem here? So keywords here: training accuracy oscillates, many batch training, and what's the probable cause for that. So we did cover that. We did cover that on our previous slides. And while training deep learning networks, we need to look into learning rate and batch size. And when the learning rate is high, then this might like help us overshoot the correct solution and to miss outliers, and the training accuracy will oscillate. So as a rule of thumb, when training the deep neural network, we should opt for low learning rate and low batch size. And if we look into the options here, option A, the validation error has stopped decreasing. Option B, the many batch size is too small, which is good. The many batch size is too large, or the learning rate is very high. Because they are telling us that training accuracy oscillates, and when training accuracy oscillates, this means the learning rate is very high. So option D is correct. Question 5, they are telling us a machine learning specialist has created a deep learning neural network model that performs well on the training data, but performs poorly on the test data. So we have an overfitting problem here. Which of the following methods should the specialist consider using to correct this? Have to choose 3. So here they are telling us that they are creating deep neural networks. This is the first keyword. It performs well in the training data, but performs poorly in the test data. So we have overfitting problem here. And when we have overfitting, we can think of increasing regularizations as to add L1 or L2. We can think of adding dropout. So if we go into the options we have, we need to choose 3. Decrease regularization, which will not help reducing overfitting. Increased regularization would help reduce overfitting, so option B is correct. Increased dropout also would help. Decreased dropout wouldn't help reducing overfitting, because we need to increase dropout in order to make the model learn the patterns of the training data and learn the patterns of training data properly and have a good performance test data. Increase future combinations or decrease future combinations. And here, because the model is learning the training data well, so we need to think of reducing the feature combinations, which make the model more simple, which help it like learn the patterns better on the training data. And when we give it the test data, it will give the same performance. So it wouldn't overfit. So in this case, we should definitely choose option B, increase regularization. We should choose increase dropout, and we should also think of decreasing feature combinations in order to make the model to perform good on the train test and the test set as well. Question 6, they are telling us you work as a machine learning specialist for a small startup. The founder of the company needs you to quickly build a model to test one of the team's minimum viable products or MVPs with the intent of preserving or pivoting depending on the outcome of your model experiment. You have decided to use SageMaker Autopilot to create your experiment. You have selected the S3 bucket, data source, and target feature for which to make predictions. You are now ready to select the machine learning problem type and objective metric. Which are the viable combinations for your selections? So keywords to think of here is we need to use autopilot, and we need to select the data source and target feature to make predictions. So, and they are telling us that we need to we need to help the team who's building the MVP to use the model depending on the outcome of our model experiment. So we have to choose the correct problem type and the problem objective matrix. So if we look into the combinations here, problem type multi-class classification, object AUC. Problem option B, regression objective F1. Option C, binary classification objective MSE, which is mean squared error. or option D, regression, objective mean squared error. So if we look into the options, the most compatible one would be to choose regression. And within regression, we can choose mean squared error, which is one of potential potential performance metrics for regression. So option D is correct in this case. We can use regression, and for regression, we can use mean squared error as our objective metric. So this takes us to the end of this video, where we did talk about modeling in depth, which is the most important section of the AWS ML examination. However, you need to go further. You need to read more about each of the topics we talked about and make sure you are confident on answering any of the questions that come through your way in the examination. The next video, we will talk about the last section, which is the ML Ops. Until then, happy studying, and thank you for watching.